Hello. So in this video, I'll be going over the derivation of the moment of inertia of a spherical shell where the axis of rotation is through its center. So unlike in a previous video I've done where I've gone over the moment of inertia for a solid sphere, this is just a shell, so nothing is in the interior. Okay, so in the top left corner, I've drawn out our system, which is a spherical shell. I've given it a thickness of dr, which is some infinitesimally small thickness, and I've put our spherical shell at a radius of capital R away from the origin. In this setup, I've made it to rotate about the z-axis, although it can be any axis that passes through the center. So before I begin the actual derivation of the moment of inertia of a spherical shell, I'm going to go back to the moment of inertia of a solid sphere, which I derived in a previous video, but you can also look up. And this will be rather critical in the derivation of the spherical shell that I'll be doing. But to go back, the moment of inertia of a solid sphere where the axis of rotation is through its center is 2/5 mr squared. And here I've written it as a function of r just to emphasize the dependency on radius. Expanding out the mass term of the solid sphere, you can write it as rho times the volume, where the volume of the sphere is 4/3 pi r cubed. And here I'm taking rho to be the volume density, or mass over volume. And from this expression, you can condense terms to write it as 8/15 rho pi r to the 5th. So that is the moment of inertia of a solid sphere. To get the moment of inertia of a spherical shell, what you can do is first differentiate the moment of inertia of a solid sphere with respect to radius. And that you get as 8/15 rho pi 5 r to the 4th. And conceptually what this is how the moment of inertia of the solid sphere is changing with respect to radius. So if you add a little radius, this is how much the moment of inertia is going to change. And what I've never been too sure about how mathematically correct this is, but I've seen it a lot in physics courses, so I will also be doing it. And conceptually it makes sense. So you can move the dr in the denominator to the other side of the equation and write di is equal to 8/15 rho pi 5 r to the 4th dr. And this relates the little bit of moment of inertia gained when you also gain a little bit of thickness dr. And what this di actually is the moment of inertia gained when you add a little shell. So from this, we'll be getting our moment of inertia of our spherical shell. So the mission now is to get rid of rho. So just to get our moment of inertia in a more clear form. So rho is volume density, so I need a volume term. And we're dealing with a spherical shell, so multiplying by a clever form of 1, that being 4/4, I can rewrite this expression as 8/15 rho 4 pi r squared dr 5 r squared times 1/4. So I've multiplied by 4/4, as I said. I have split up the r squared, I've split up the r to the 4th into 2 r squareds, and I've grouped all these terms together of rho 4 pi r squared dr. So that term there is going to end up being our volume of the spherical shell, and that's coming from 4 pi r squared being the surface area of the shell, and then dr is its thickness. So just combining some coefficients together, we can end up with the expression of 2/3 rho 4 pi r squared dr r squared. And as I said before, 4 pi r squared dr is the volume of our spherical shell, and we're going to be taking the same volume density as this solid sphere, although that's not too important. But from there, we can write rho v as mass. So di is 2/3 mr squared, and that di is the moment of inertia of the spherical shell. So the moment of inertia of a spherical shell, where the axis of rotation is through its center, is 2/3 mr squared. I hope that you enjoyed the video, and thank you for watching it. If you have any questions about it, please comment, or if you have any suggestions for future videos, please also comment with those. Thank you.